Okay, good afternoon. We are starting the last session today. The first speaker is Antoni Szczurek, who will talk about central dilepton production in proton-proton collisions with rapidity gap and with forward protons. Antoni, please go ahead.
Thank you very much. I hope you are relaxed after this long break we had. And now we can continue. So the title was given. So the work is done together with the chairman and Barbara Linek, who is PhD student of Marta Uszczak. So I will continue. So content of my talk, I will be talking about inclusive production a little bit. So show some integrated cross-section distributions, say a few words about structure functions. Then I will go to the case with the measurement of proton. So this is the case when cuts on psi variable are imposed. Then I will discuss a range of Bjorken X, which is tested in such processes. Then I will talk about jets and hard emissions. And then I will say a few words about results based on supersheet, which we have done, where we also look at the differential gap survival factor. So I will be talking about photon-photon fusion as the dominant mechanism. And as was said, both Atlas and CMS performed some relevant measurements with forward protons. So we concentrate on this case with one forward proton. So far, two forward protons cannot be measured. So I want to say that our group was really, in my view, was the first who proposed to use the formalism of photon with transverse momenta. So this is very similar to KT factorization. I will say a few words about this. And the same formalism can be used to production of other issues. I think Lucian Harland-Lang was talking about this in a parallel talk, which was in another session. Here we want to discuss this proton measurement, how much it changes differential distribution, rapidity gap, and so on. And finally, I will show some results with supersheet, which has soft gap survival factor included in it. Here I am showing this our papers on this subject. So we really started 2015 with Da Silveira, Fortom, Piotrkowski, and Wolfgang Schäfer, and then continue with Marta. And this was about leptons. Then we went to WT production in this last paper. So I will be talking about four different mechanisms, but four categories of mechanism. One is fully elastic with both protons in the ground state. There is also inelastic component. So two protons dissociate, and I will consider mostly such cases with single proton emission. So this is exactly which correspond to the measurement, to recent measurement of Atlas. So as I said, I will do calculation in something which can be called KT factorization approach for photons. And in this approach, we have unintegrated photon distributions with transverse momenta, which is bold Q in one proton, in a second proton, and off-shell cross-section for such process. I will not show formulas because there is no time. I will only say that there are two kinds of such fluxes, one which corresponds to elastic vertex, and second which corresponds to inelastic vertex, and different combinations are possible in principle. Sometimes it is sometimes it is some contributions are selected by experimental conditions. So X value in the fluxes can be calculated from kinematics. This is written here. And what is really important is four momenta of photons. So here, in addition to longitudinal parts, there is also transverse parts of four momenta which form transverse momentum of the produced system. So actually this method was proposed by Budniew, Ginsburg, Serbo, and something else, which I have forgotten, really long ago. So in this approach, elastic flux is expressed, elastic flux of photons, of course, is expressed in terms of proton electromagnetic form factors, whereas inelastic flux is expressed in terms of structure functions. Long ago, those structure functions were not extremely known. Now they have been measured in the broad range of X and Q, so we really know them. This F I called unintegrated photon distribution, but one can consider even doubly unintegrated photon distribution, which depends also on the mass of the remnant. And actually, in the full calculation, I will use this doubly unintegrated photon distributions. Actually, those distributions were used in our papers for W plus W minus and TT bar. Actually, protons can be produced also from the remnants, but usually those protons have a much smaller longitudinal momentum, so they are not measured. The only case they can be measured are such diffractive processes, which I have shown here. So this is Pomeron exchange, there's Pomeron remnant, and this proton loses not much energy, this or that. However, such processes produce Pomeron remnants, which would appear in the main detector, and such processes I think can be discarded, although such processes were not really calculated. I want to say that there are also diffractive photon distributions, which we think are much smaller than usual inelastic photon distributions, but honestly, this was never calculated so far. Kinematics, so arguments of the structure functions, so this is Bjork and X for one or second proton, and photon virtualities. I will be talking about those variables because this is really important in this context. So actually, as was mentioned by Jesse, Atlas measure such Xi plus and Xi minus, which is totally based on lepton variables, on lepton mass and lepton rapidity. And we will also, in our calculation, we will also use such lepton variables. So in our approach, we have to make multiple integration. So this is really integration over 9 or 10 variables. And this is done in Vegas method. So these are variables which we use for integration. So these are transverse momenta of photons, but also masses of the remnants of one proton or the second proton. And actually, these ranges of these variables must be carefully adjusted, and these transverse momenta are large for inelastic contributions, and also invariant masses are large, and depending on kinematics, there should be in such ranges. So our results, I will go slowly to results. So we are using more or less kinematical cuts. So these are transverse momenta for leptons and rapidity range. We also use experimental cuts on Xi plus or Xi minus. However, we do not include exclusion window for Z boson, as was done in experiment, and we also not put cuts on lepton accoplanarity. We really want to demonstrate some effects. We don't want to make direct comparison to the Atlas measurement. So what can we do? We can do many measurements. We can calculate invariant mass distribution of the dilepton pair. So this is one distribution. Very interesting is the distribution, two-dimensional distribution. Here is rapidity of the lepton pair and mass of the lepton pair. Here there is results without cuts on Xi1 and Xi2. And as you can see, there is maximum here. You will see how it changes when we go to the proton measurement. Xi distribution is peaked at a very small Xi's. So therefore, if we put some window on Xi, we kill a lot of cross section. So the cross section with proton measurement is really much smaller than the cross section without the proton measurement. Here I am showing this for double elastic contribution and two-dimensional Xi on the one leg and Xi on the second leg. Such distribution, this is logarithmic scale, such distribution drop quickly. So really cuts will kill a lot the cross section. As I mentioned, really large invariant, really large masses of the remnant are produced. So this is 1 TeV. This is shown from 0 to 1 TeV, shown from different distribution. Abramovich-Levy, Szczurek-Ureszczenko, but only partonic part, and looks like distribution which is very popular recently. Here we show also some contribution of resonances, which I will discuss shortly in the moment. For single dissociative contribution, we can also calculate mass distribution in invariant mass of the dileptons. This is similar distribution in Xi for this case. It is similar to elastic case. Here I am showing distribution. This is for single dissociative contribution and distribution in transverse momentum of the intermediate photons. As you can see, really large transverse momenta enter such calculations. And previously, such calculations were done in the collinear calculation where those transverse momenta were put to 0. So this is really essential to include those transverse momenta because they are huge. Here I am showing some kind of correlations for single dissociative contribution, correlation between transverse momentum of the photon and associated mass of the remnant system. So you can see if we go to large remnant systems, masses of the remnant system, then we produce large transverse momenta of the photon. This is really crucial correlation. This is without Xi cuts and with Xi cuts. I will not discuss this more. So we impose such cuts, and this figure only shows that we did it for different contributions separately because this is theoretical calculation. Here I am showing cross section. I don't want that you.
You have 3 minutes left.
Wow. So really. Without cuts, we have large cross section. When we go to cuts, cross section is much lower. And in addition, if we put cuts on transverse momentum of the pair, as was done in experiment, then the cross section is even much smaller. Here, maybe I will then skip and show that if we impose cuts, then the distribution in rapidity of the pair has such a dip. And actually, Jesse was showing such a result with where this dip was clearly seen. This figure is maybe interesting because it shows what axis we probe in such processes. So this is Bjorken X for single dissociative process, and this is without cuts on protons, with cuts on protons, and this in addition shows contribution of resonances, which we explicitly include in our calculation. What are Q squared, which are important for structure function? They are really in the broad range of Q squared, as you can see. So there is region, non-perturbative region, but also perturbative region of structure function. So one has to be careful about models of structure functions which are used, and actually different parametrizations are on the market. But I think this was not deeply tested really, because different of them are good for some regions and some are important for some other regions. So there's no one set which is equally good for all regions. So of course, if we we can include also we can calculate distribution of jets for such case, and these are distributions of jets without cut on proton and with cut on proton. They are not dramatically different, but they are dramatically different if we put cut on PT of the pair. And now I will go to super chic calculations, and I want to show the result of gap survival. We did such calculations, and I will show gap survival and maybe concentrate on this block. So you see that for elastic scattering, gap survival is relatively large, and this is much smaller for inelastic case where it is about 0.7. If we put cuts in addition on proton, then this gap is even lower and is about 50%. I will not discuss this more. And now I want to show some distribution, some rapidity. We calculated gap survival in super chic. Here you see distributions. There are fluctuations because statistics was not extremely large in this calculation. And I will directly, we calculated different distributions with gap survival, without gap survival, with cuts on Xi, without cuts on Xi, and we calculated gap survivals, which are just calculation with soft gap survival effect included and divided by the cross-section or distribution, differential distribution without gap survival. And here I will show such distributions quickly. So this is gap survival as a function of an invariant mass of the dilepton pair. There is some effect, however, fluctuations are so big that one cannot see this effect clearly. With cuts, this gap survival is smaller. We found interesting effect of rapidity gap as a function of rapidity of the dilepton pair. So you can see here that there is clear dependence of the gap on the rapidity of the pair. In the case when we do not include cuts on proton, if we include cuts, this dependence disappears. So there is a second effect, which is also related to gap effect, which is related to jet emission. So this is jet this is calculation from super chic, the distribution of jets without cuts on proton and with cuts on proton. So this effect, imposing cuts, causes that these jets are moved to the region of the main detectors, and therefore this will be the last transparency, which I am going to show. And you can see that there is additional cut when we put cuts on Xi1 or Xi2, when there's extra survival factor, which is 0.49, due to the fact that jet is going to the main detector and I can use veto. So, and this, so again, this kind of gap survival, which is in addition to soft gap survival, look here, it is much smaller when the cuts are imposed compared to the case when cuts are not imposed. So I think I will go to the conclusions. So we have presented calculation of dilepton production with one forward proton. We also discussed for us a double dissociation process, but we came to the conclusion that it gives negligible contribution. In addition, which I had no time to discuss, we included resonances, delta resonance or some other nucleon resonances, which are usually not included in standard parametrization of the structure functions, and they can give some contribution of the order of 10%. So I think I can stop here. We have found interesting effect of the gap survival on rapidity of the dilepton pairs. I think I will stop here because I was talking too long. Thank you.
Okay. Okay, thank you, Antoni, for a very interesting talk. Now we have questions. The first question is from Francesco. Francesco, go ahead.
Thanks. Hi, here is Francesco. Thanks, Antoni, for this very nice talk. I would like to ask a very simple and naive curiosity. In particular, how do you build this unintegrated photon distribution? Is there any evolution driven? Do they respect any evolution or not? Just to understand. Could you emphasize this? Thanks.
Yes, thank you. Thank you. So actually what we do is if you look at this first diagram, so you will see that it is very much the same as the diagram for deep inelastic scattering. So we can, of course, in deep inelastic scattering, you can just use experimental structure function, or you can try to use to fit structure function using evolution. So our idea was not to do any evolution because we thought it is unnecessary. We can use structure functions as they are known. So we used parametrization of experimental structure function. So of course, such effects are included there, but I want to say that there is also a region of non-perturbative physics where there are some other effects except of evolution. So, so the situation is very complicated. So this region of X and Q square we are probing in such processes is very specific, and I try to show that we try to understand really which regions of X and Q square enter such calculations. And so this is not that somebody has fantastic perturbative structure function and puts to the calculation. It is not enough because they are both perturbative and not perturbative regions, and one has to be really careful. This is my warning.
Okay, I understand, and there is also this non-perturbative content that has to be taken into account. Thanks.
Thank you.
Thanks. We have another question from Wojtek Gurin.
Please.
Hello. So I just wonder if your calculations can apply to what we heard from Atlas talk earlier, and I guess it would be your elastic or double elastic case.
Thank you. Absolutely, it can be used. So actually, both elastic and single dissociative processes contribute in the Atlas case. But as I said, Atlas put some extra cut in this paper, this physical review letter, puts extra cut on PT of the pair, and it is not too big when those gap survivals are not are relatively large. But we have shown that if you remove this condition of small PT of the pair, then those gap survivals are much bigger. So actually it would be very interesting if Atlas measures this larger PT pairs, and actually one could test if we understand those gap survival, because this is one thing which was never tested to my mind, and it would be good if Atlas could really go to this region and then one could test gap survivals.
Thank you.
Thank you. The last short question is from Rainer.
Yeah, thanks, Antoni, for a wonderful talk. Now, you made a point in stressing that you need the transverse momentum of the photons to explain or to understand the data from muon pairs. And that transverse momentum comes in through what you call the doubly unintegrated photon distribution.
Exactly.
Now, in real life, you know that the two protons that carry the photon flux are not collinear. They come at an angle with respect to each other, which in fact actually leads to the fact that the
outgoing protons.
No, the incoming protons. They have a beam. There's something called beam divergence.
Yes, yes, yes.
Particularly if you run at high luminosity.
Right.
Have you estimated that effect when you squeeze the beam? In other words, that the center of mass system of the two protons has a brings in a transverse momentum.
Yeah, that's I think it may be important experimental issue. I personally I didn't study this effect. I think if one concentrate on the region of large Q, then one can neglect this effect. But if one selects sample with small Q, maybe it should be checked. So thank you for this comment. We haven't done this. Maybe it requires a check.
Yes, I agree. If you go to large QT, then probably
this is negligible compared to large Q.
Rainer, you are muted.
Yes, I have, because of to avoid the echo.
Oh, okay.
Well, we talk offline, Antoni. I think is
yes. Thank you.
Is an effect that one should be aware of and take into consideration.
We can estimate it.
Okay, let's thanks the speaker again. I suggest that we move to the next talk. The next is Rafal Sikora. Rafal, could you share your screen?
Okay, can you see it? Can you hear me also?
Yes, we can hear you. Okay, you can start.
Okay, thank you. I would like to give the talk on behalf of the Startup collaboration with the recent results on central exclusive production. A brief introduction to the process. So we talk about the central exclusive production when we have two incoming particles that stay intact after the collision, where eventually they may become excited, but they form a central state X that is separated from those outgoing beams or the remnants with the rapidity gaps. We can generally divide the production mechanisms into three cases. The first one, the double photon exchange. The second, the photoproduction, photon pomeron. Or the third one, fully hadronic, the double pomeron exchange. That is the topic of our main study. In this talk, I would like to discuss the measurement of the charged hadron pairs. So the central state X consists of two hadrons oppositely charged with the detection of forward scattered protons. And this is something which makes this measurement particularly important. As I said, we measured two particles in the central system. So this process is generally simple in terms of topology, but in terms of theory, it's quite complex. We know that the pomeron in QCD in the perturbative image is a pair of gluons, so it is commonly believed that glue balls should be produced quite numerously in double pomeron exchange. So that's one thing that makes this process interesting. In the low mass range that we study here, there is no hard scale, so we are forced to use phenomenology in description. We cannot use PQCD. Not only this, the cross sections are suppressed and modulated by the absorption effects that are marked on the left diagram with those gray ovals. And this absorption is on top of the quantum interference because we can have contributions from amplitudes describing the continuum production when the hadron, the virtual hadron, is exchanged between the pomerons, or the resonant production where the two pomerons directly couple to the resonance that further decays into the pair of hadrons. So there are plenty of phenomena. And at the time when we prepared the paper, there were three phenomenological models on the market describing the process. The first one from the Durham group implemented in DIME generator, the second from the Krakow group implemented in GenX, and also MBR model in Pythia 8 that was tuned to central diffraction, inclusive central diffraction data on CDF. Generally, the parameters of those models are poorly constrained, and that's why our data seems to be important to provide to better constrain the free parameters. And those models, by definition, are not able to describe our data because these are models of continuum. Our data has everything, so also resonances, but we decided to compare it just for the completeness and for the further references. I would like to move to physics so fast, so I will not describe the details of our selections. In general, we measured two central particles in the TPC and 2 forward protons in the Raman pods, 1 on each side of star. And we placed some cuts on PT, on eta, and on transverse momentum components of the forward protons to stay in the fiducial region where we know our acceptances and efficiencies best that allow us to reduce maximally the systematic uncertainties. What I want to highlight is the fact that the minimum PT of the forward protons that we measure is 0.04 GeV squared, which basically cuts off all the contributions from the photon pomeron, which is also further seen by the lack of rho-0, for example, in the mass spectrum. We divide the backgrounds into several categories. The main background that we must deal with is the background with from the central diffraction process. So the process in which we have 2 forward-going protons and the more than 2 particles in the central system, of which some are just not detected because of the inefficiency or because of the limited geometrical coverage. But because we measure also forward protons, we are able to form the transverse momentum of the entire 4-particle system, and this is drawn on the left-hand side. You can see that this total momentum is peaked at 0, which corresponds to our signal, and there is not much background under the signal peak, which we determine from the data by extrapolating from the signal region from the signal free region to the signal region. And on the right-hand side, you can see that the row counts for the channel where 2 pions are produced in the central system, and this background is shown with magenta. You can see by eye that it's small, and for pi and kk pairs is less than 6%, and for pp bar is 12%. So we really managed to limit the background contributions to the minimum. Now the physics results. Before I discuss the spectrum, I would like to point out the systematic uncertainties that are marked only on a few points with the gray boxes. We draw it only on in few places to highlight that these errors are strongly correlated, and they should be understood as allowed collective movement of all the points upwards or downwards. So they should not be treated as statistical uncertainties which are uncorrelated. And those systematics are 4 times better than the double Pomeron exchanged measurement with the forward going proton tagging until this day. That was done by the ISR at the ISR collider. Now moving to the distribution, to the cross section, there is a dip around 0.5 that comes from the fiducial cuts. So this is acceptance effects. Then we have a peak at 1 GeV followed by a sharp drop that we attribute to F0 980 resonance. There is a peak between 1 and 1.5 that we attribute to F2 1270 resonance. And then we see a resonance like around 2.2 GeV, yes, which we did not identify. We also show on the plots, on this plot and the further plots, the continuum predictions, and we generally attribute the DIME, which is green, as providing the best description of our data. I want to also add here that only this DIME generator contains the absorption effects in it. For the GenX, we scaled the prediction by 0.285, which more or less corresponds to the expected size of absorption. And Pythia predictions are scaled by 0.25 also, just to have correct, say, scale compared to other predictions. Now let's move to the next slide, where we show the 2 other channels that we have measured. So on the left-hand side, there is the cross section as a function of the invariant mass of the pair of the system that contains a pair of kaons, and on the right-hand side, PP bar. Regarding the kaons pairs, we see an enhancement in the F2 prime region and F070 1310, and also some peak around F2 1270. On the right-hand side, we see we can compare the PP bar with the Pythia. That from the plot you can see that Pythia overestimates the cross section for PP bar by the factor of 8. Now we show the differential cross sections also as a function of observables related to the forward going protons. This is by design possible only if those protons are measured. So here is an azimuthal angle in the transverse plane between the two protons. I want only to say that this dip around 90 degrees is due to the fiducial cuts. We see significant asymmetry, left-right asymmetry. However, this asymmetry seems to be well described by the DIME generator that contains absorption. So this smaller cross section at delta phi greater than 90 degrees is attributed to the stronger absorption in this configuration of the forward protons, just because we can conclude it from the comparison with DIME, which has this absorption in it. Given the information of the forward system, here we show the property of the central system, the invariant mass, as a function of the, well, in two ranges of those delta phi, of this delta phi angle between the forward going protons. So on the left hand side we have this angle less than 90 degrees, and on the right hand side we have this angle greater than 90 degrees. We see clear differences between the data points. First one is that on the right hand side we do not have data points below 0.5 GeV, and this is because of the fiducial cuts. And then we see that for delta phi less than 90 degrees, the F0 980 peak, as well as this resonance structure at 2.2 GeV is more pronounced compared to delta phi greater than 90 degrees. And it is opposite for the peak around F2 1270. So F2 1270 seems to be produced more dominantly at this delta phi greater than 90 degrees. Now we also show the cross section as a function of the Mandelstam T. This here the sum of Mandelstam T's of two protons for all the channels. We can generally conclude that the best description of the T spectra is provided by DIME generator, and Pythia also works fine, except that for the forward for the PP bar channel, Pythia has too steep slope. We have also studied angular distributions of the central state particles for the pi plus pi minus system. So in this slide we show the azimuthal angle in the Collins-Soper reference frame for the positively charged pion in three regions of the invariant mass of the pair. So the left-hand side plot is for the mass below 1 GeV, the middle is for the mass between 1 and 1.5 GeV, on the right-hand side mass above 1.5 GeV. In the lowest mass region, we see that the data points are quite well described by the pure S0 wave.
Rafal, you have 3 more minutes.
Yes, thank you. In the middle plot, we see that the data points are reasonably well described by the pure D0 wave, and this is consistent with the peak from the presumably F2 1270. And the right-hand side shows that the data points in the right-hand side plot cannot be described by the single wave, which suggests that either there's a mixture of wave and also possibly higher waves. We didn't limit to ourselves to the fiducial cross sections. We have also done the extrapolation of the cross section in the invariant mass for the pi plus pi minus. So we extrapolated it to the Lorentz invariant phase space given in blue. And then we have fitted it with the minimal model. This minimal model contained the coherent sum of the continuum and 3 resonances, of which we only assumed, we only fixed the mass and width for the F2-1270. The remaining 2 resonances were left free, and it turned out that the spectrum can be well described with the parameters of those 2 resonances being consistent with F0 980 and F0 1500. With the last one being enhanced in the region of the small delta phi that seems to be in correspondence with the expectation for the, say, global production, because this delta phi close to 0 means a low relative momentum of the 2 pomerons, and it is expected that in such configuration the global production should be enhanced. Also, we have fitted a double differential cross section as a function of the Mandelstam T's with the exponential functions to extract the slope b, which should help to constrain the parameters, for example, of the Pomeron Meson couplings. But the interpretation should be left to theory developers. And maybe some teaser. We have also results from 510 and 10 GeV to come. You can see the invariant mass spectrum for the pi-pi pair on the left-hand side for the 2 configurations of the forward-going protons. Generally, the features of those spectra are in agreement with the 200 GeV results. The statistics may be slightly better, so please stay tuned for those results to come. Let me summarize. So we have measured the central exclusive production at 200 GeV and 510 GeV. So for the 200 GeV, there is a paper published in JHEP, and at 500 GeV, there are preliminary results for now. These are currently the highest energies in which this process was measured with the forward proton detection. We have selected samples of pi-pi, KK, and pp bar. We calculated cross sections. We observed some structures in the spectra that we attribute to known resonances and some resonance at 2.2 GeV. And we performed comparisons with the models. Hopefully, those results will help to better constrain the parameters of the models. Thank you for your attention.
Thank you, Rafał, for a very nice and very interesting talk. Thanks a lot. Questions? Okay, the first question is from Antoni.
Hello, Rafał.
Hello.
Very good talk indeed. I wanted to ask you, because now you have this 500 GeV data. So we have a unique prediction from tensor Pomeron model that if you look at the distribution in difference in rapidity of proton and antiproton, it should have 0. It should be a dip at 0. So
yes.
If you are still analyzing the data, please make such a plot.
Okay, yes, the analyzer for 500 GeV is somebody else. It's Tomasz Truchlarz from Prague. The problem with the difference in rapidity is the limited pseudo-rapidity coverage of the star detector.
I know, but nevertheless, it would be nice if we see sign of the.
Yeah, I think Atlas has better chance to do this.
That's absolutely.
Rainer?
Yeah, I wanted to ask you about the comparison of the 200 and 500 GeV data. I see a big difference in the kaon spectra.
Yes, so the case is
that you have a very strong signal at 500 GeV in the invariant mass, K plus K minus of the phi, and that is absent in the 200 GeV data.
Yes.
You understand that?
We
have an explanation for this?
we have possible explanations. So the first one is that those plots that I show you now do not have the background subtracted, okay? Non-exclusive background, which is the dominant one. And at 500 GeV, the fiducial region changed a lot. So the minimum PT of the forward proton is such high that potentially many phi-phi events, so the double phi production, enter into our spectrum. So possibly this is related to the different T range. So possibly at higher T's, the amplitude for the phi production is higher. So that's one explanation. Another is that this is background from the 2 phi production when 1 phi was not detected and the other enters into our acceptance. So this is still work in progress.
Can I ask a follow-up question? Shouldn't that be this background due to double phi? Shouldn't that be cut out by your missing PT cut?
Not
I mean, here what you show on slide 12, do you have this missing PT cut applied already?
Yes, but missing PT cut does not do the entire work. So you can see on the left-hand side the missing PT integrated, right? So it may be that in some mass range, this background is much higher relative to the signal peak, and it should be subtracted. In the 200 GeV results, we have it subtracted differentially. In 500 GeV, it's not subtracted at all. So it's still work in progress, and this peak may disappear once the background is subtracted. Okay, but I can't say definitely.
Well, okay, thank you. Looking forward to your next talk. I mean, yeah, sometimes next year, whenever the data is analyzed and background subtracted.
Okay, thank you. We have another question from Lucian Harland.
Hi, yeah, thank you. It's a very nice talk. Yeah, it just occurred to me for your various comparisons on, well, let's say slide 7, for example, that it's a simple matter to provide the time Monte Carlo with survival factor turned off, because I think you basically show the comparison in effect by comparing with GenX, as you say, where it's right. The differential part of it is not included. But you know, in the future, if you're interested in that, we can certainly provide that. It's an easy thing to do. I mean, for the published data, that's a job for us, I guess. It's just be another way of showing that point nicely, I think.
Okay, thanks.
No worries.
Włodek?
I have a comment first to Rainer in terms of this phi peak that you see. One has to be very careful making any predictions by seeing the spectrum close to the threshold. As you can see, this is the left edge of this is close to K plus K minus threshold. So you can think about various interpretations, but as Rafal pointed out, this is a work in progress and requires more analysis. And all I want to do is to caution you that it is close to threshold. So that peak could be just an artificial thing. So we don't know what it is, but it may not be what you think it is. And
well, yeah. I mean, the other question I did not dare to ask, but which I have to raise now. In this community doing central production at low masses, the question is, what is the acceptance, or what is this distribution two-dimensionally, the mass of the kaon pair versus the PT of the kaon pair? That would be an interesting presentation. You know, this goes back to the days when data were taken at CDF, Mike Albrow and his groups and his collaborators.
Okay, thank you. We'll try to do that. It's as you say.
In first order, it's done by plotting the mass versus delta phi, because delta phi less than 90 degrees means the elastic-like configuration of the forward going. Sorry, less than 90 degrees means anti-elastic configuration of the forward protons, so high PT of the pair. And the delta phi greater than 90 degrees means elastic-like, and the pair has very low PT. So that's the first order comparisons that you can do from the available plots.
Okay, thank you very much. We can continue with the next talk. The next speaker is Francesco Giovanni Celiberto. Francesco, could you share your screen?
Yes, hello, can you hear me, Marta?
Yes.
Okay, let me share. Can you see slides?
Yes, we can see.
Full screen now?
Yes.
Okay,
Perfect.
okay. Before to start, I would like to Thanks. Before to start, I would like to thank you, the organizer of this nice conference, is also the convener of this session, to give me the possibility to discuss and present results on exclusive emission of rho-mesons as a discriminator for different models of the integrated Gluon distribution, and more in general as tool to access hadronic structure at small x. Before to go into the details of our study, I would like to briefly mention some different way to access hadronic structure at small x. And in spite of the title here, it is a very incomplete list of small x formalisms, which are all of them based in the linear approximation on the BFK evolution, or in the non-linear approximation to the saturation effects described in terms of the decay Gene-Walk evolution equations. So let us start by the unintegrated parton density, in which we can establish a high energy factorization. We will see that this factorization can be hybrid, so in terms of an integrated distribution and also collinear PDF. And as I told you, the main ingredient is the BFK resummation, which help us to define an integrated Gluon distribution, in which we have the description in terms of regions. And here an integrated Gluon distribution is driven by the pure small x evolution. Then there are other approaches like high energy factorization of la CCFM or partonization approach, which help us to describe an integrated PDF in which BFK is matched with a collinear ingredient. Then the second possibility is the determination of small x improved collinear PDF, in which we consider standard collinear PDF, but with a small x resummed splitting. And in 2018, we had the first determination of this kind of an unpolarized PDF. The third way to access hadronic structure is our model calculated together with the Pavia group, that we call small x improved Gluon TMDs, in which the non-perturbative content in the TMD is introduced via an enhanced spectator model, and we fitted the integrated TMD to initial scale unpolarized transversely polarized helicity PDF, and we performed the first determination of this model just last year. Then it is worth to mention the way to access at small x helicity and orbital angular momentum via subiconal correction, which are generally integrated by BFKL, but are introduced by the Baliski-Ermolaiver-Riskin approach, and also by the Kochekov-Pitoniak-Sievert approach formalism. And then, just to mention, it is important to know the color glass condensate Gene-Walk Gluon TMDs, in which Gluon recombination effects are encoded, and we are able to distinguish between two main kind of the TMD distribution, WW and dipole, and then the improved TMD framework, in which there is an interpolation between the TMD approach and the BFK regime. We will discuss today about an integrated Gluon distribution calculating the BFK approach that we call all twist high energy factorization, because all twists are included here. Just to clarify the difference between, for example, TMD formalism and BFKL or all twist high energy factorization, we recall that in the TMD formalism, we are able to describe semi-inclusive processes in which the observable KT is much smaller than hardest scale. And this kind of distribution speaks the language of parton correlator. And here we see as a representative diagram the production of a quark-onium state in series configuration. Then, for example, when we speak about an integrated Gluon distribution, we can describe both inclusive or exclusive processes. This is important because the same distribution can go inside the amplitude if the imaginary part of the amplitude, if we describe exclusive process of directly the cross-section via the optical theorem if we describe inclusive processes. And the regime in which we can probe this, we can define and probe distribution is small x and large KT. There is a difference in the fact that here we consider not anymore the parton correlator language by the diagrammatical approach in terms of regions at Gluon. And here, this is a striking feature. Even a fully inclusive process like DIS is described in terms of this unintegrated Gluon distribution. In which way? We consider the standard factorization given by BFKL as a factorization between the impact factor for the transition gamma star to gamma star, the BFKL forward gluon ladder, which allow us to describe evolution small x effects, and then a non-perturbative quantity, which is nothing but the proton impact factor. And here we have to make some remarks. In particular, this factorization holds, as I mentioned, at large KT. But in fact, since we are inclusive on KT, there is an integration. I don't show here the formula, but there is an integration over the whole spectrum of KT. So it means that this convolution has to pick the large KT region. This is possible because thanks to the theorem by Fadin and Martin, the colorless impact factor are infrared safe. So they go to 0 when KT is small, and we can perform safely this KT factorization. And then there is another issue that I want to mention. There is the so-called infrared diffusion pattern, because here when we go from the perturbative scale, which is the virtuality of the photon, to a scale that is representative and is characteristic of the proton impact factor, which is non-perturbative, we go from large scale to small scale, which in principle could be and are in the non-perturbative region. So we observe some diffusion pattern here, and there is an open question, and we have to understand how to improve the description by minimizing these diffusion pattern effects. Then inside the high energy factorization between impact factor and gluon impact factors and unintegrated and BFK ladder, we can recognize the unintegrated gluon distribution, even in the case of virtual photoabsorption. So in DIS as the lower subfactorization. So we have a convolution between the BFK gluon ladder and the proton impact factor. And in this small x limit, these represent nothing but how an integrated Gluon distribution. The BFK Gluon ladder, as we know, takes into account the resummation of high energy logarithms, by the proton impact factor describes the coupling of the gluon green function to proton. Since the impact factor is non-perturbative, the whole UGT is partially a non-perturbative quantity, it has to be modeled. And there are some models which are defined during the years and were proposed to the community. And here I mention an incomplete list of them. For example, this model, which is an X-independent model, we can simply take the gluon momentum derivative. Then we have the Ivanov-Nikolaev model, in which we can probe both the different region of KT via soft plus hard strategy. Then we have the Enchinsky-Piovera-Salas an integrated Gluon distribution, in which we convolve a la BFKL the gluon ladder with a model for the proton impact factor. Then we have the WMR, in which there is angular ordering of gluon emission, and it is based on CCFM. And then we have the GBW parameterization, which encodes saturation effects. And here we see in this plot that all these models show a distinctive and different behavior on KT. So we expect a strong sensitivity of our observables on these models. Just another introductory slide about the factorization. We can have, as I mentioned, hybrid or pure factorization. And for example, if we consider forward emission in PP collision, we have an asymmetric configuration in which the fast parton, there is on one side a fast parton and on the other side a small x gluon. While in central emission, when we consider gluon-induced process, we pick both small x gluons. And we see better in the next part of the slides, in which we can combine a hybrid high energy collinear factorization here, and here a pure high energy factorization in terms of an integrated Gluon distribution, while in this case, the fast parton is described in terms of a collinear PDF in red. And here we expect in the forward emission distinctive signal of small x dynamics. And here we expect that small x dynamic is able to enhance fixed order description. And from the phenomenological point of view, here we have all the representative class of forward object emitted. And in this talk, we will focus on vector meson, or here in this case, we can have central jet, central Higgs, or vector meson. We complement this table by exclusive counterpart and leptodronic channels. And indeed, we will, in the next slide, we will see an exclusive leptodronic channel, which is the exclusive forward rho-meson leptoproduction, in which high energy regime, we studied this process at HERA, and the eigenenergy regime is given by the small x here, which the x is given by the virtuality divided by w square, and the photon virtuality, as I mentioned, it as in DIS is the hard scale of the process. The process is solved in helicity, and this is a test field for unintegrated Gluon distribution. Why it is solved in helicity? Because leading helicity amplitude are known, and we can use this assumption that the imaginary part of the amplitude is the dominant part of the amplitude, and this is valid at small x, and then we have a same W and T dependence for both the longitudinally polarized and unpolarized, the transversely polarized and the longitudinally polarized helicity amplitude, and we can expect that the same eigenenergy factorization mechanism at work. So the scattering of a small transverse size of dipole on the proton target, and we can write so in this approximation we can write the helicity amplitude for a given polarization of the photon and of the rho-meson as a high energy convolution between an impact factor and the unintegrated Gluon distribution, which is expected to be universal, doesn't depend on the process. Why in this case the distribution amplitudes describe the production of the rho-meson are encoded inside the impact factor, and we are sensitive to this helicity transition, longitudinal to longitudinal and transverse to transverse. It is worth to mention in the previous section of this of the small x DIS we had some discussion about the dipole process. The dipole mechanism. I would like to simply say here that the photon here at small x is able to see, in some sense, to probe the proton, which has a range Rp, and in general the Ioffe time, which is nothing but the coherence length of the photon, is much larger than the radius of the proton. So it means that in the expression for the hadronic tensor, at least one of these J mu current, this electromagnetic current, is outside proton. This justifies the color dipole picture in which the photon splits before in a dipole of quark and anti-quark, and then this dipole interact with the proton. And the size of the dipole is connected to the KT of one of the two quarks, for example, emitted because it is connected as a direct Fourier transform.
Francesco, you have 3 minutes left.
Many
3
thanks.
minutes left. Okay.
Many thanks. So it means that in order to respect KT high energy factorization, we have to probe small dipole size, which means large KT, through via this Fourier transform. So in our factorization, we are able to distinguish different sub-factorization. That's why I call it factorization of factorizations, because the first factorization is the BFKL1 between two impact factors and the BFKL Gluon green function. The lower part of the diagrams represents our UGD. And then inside the impact factor, we recognize another factorization between is a collinear convolution between an off-shell hard factor, described the gamma star to dipole transition, and then the convolution between this hard factor and then the distribution amplitude describing the hadronization mechanism of the rho-meson. It is important to have large KT in order to integrate over this KT and have a collinear convolution. Otherwise, we cannot rely on distribution amplitudes. And then it is worth to mention that why the longitudinal to longitudinal transition at small KT gives us a constant contribution in the impact factor. In the transverse case, here we have a divergent but integrable contribution. This is in line, this respects the Fadin-Martin theorem, but introduce some extra dependence on the small KT region, which has to be gauged. And here we see, when in our phenomenological analysis, that here, when we describe the behavior in Q square for a value of the W energy, 65 GeV provided by experiments of longitudinally polarized cross-section and transverse polarized cross-section, we see a big discrepancy, a strong sensitivity between among the different models we are used here, and none of this model is able to reproduce the whole Q square spectrum, but some of them are able to catch the intermediate Q square region. And here the uncertainty band is given in terms of the changing of the evolution parameter A2 of the distribution amplitude. These results were presented the first time in 2018 for LCT amplitudes, then extended to the case of cross-section for Meson in 2010. Then we are working together with the Cosenza collaboration and the Polish collaboration to this polarized cross-section. So I'm going to the conclusion, just a couple of slides. In the exclusive light Meson case, we see that in particular we need to have a small dipole regime to probe large KT, and this collinear factorization holds if we are in this approximation, but we saw a significance of small KT regime which is under investigation. On one side, the indication is that no large RD dynamics is at play, but the fan outcome is a sensitivity to intermediate KT, because the discrepancy between our model can be due to the, in particular, is due to the sensitivity to intermediate KT region. So we can use in general Meson, like vector Meson, to discriminate among UGD models. And I would like to briefly mention an outlook about quarkonia, in which the dipole size here gave us the possibility to describe a wide range of KT. We can describe, we can have a description in terms of relativistic QCD combined with light from wave function. We can work in the dipole limit, both in the dilute limit, both in the dipole coordinate or in the KT space. And the validity of small size dipole is questionable. In particular, larger D dynamics is expected for excited state of quarkonia. And we can use quarkonia tools as a scan for the intersection of the TMD and high energy factorization range, because smaller KT means going inside TMD regime in the case of inclusive emission. Here it is just a simple plot, simple diagram that allow us to understand that forward vector Meson emission allow us to prove an intermediate regime between and high energy factorization. And I go to the conclusion simply saying that we are interested in general to make a scan of the hadronic structure via different kind of parton density. In particular, we can provide an extensive scanning KT via forward vector Meson emission, rho-meson, but also, for example, quarkonia. Thanks.
Thank you, Francesco, for a very good talk. So do we have any questions? Yes, Farid, please.
Hi, Francesco. Yes, very nice talk. I have a naive question.
Yes.
So these UGDs, the unintegrated Gluon distributions, are the large KT limit of TMDs, right?
As far as I know, let me go to this slide, because this is quite an, actually, I thank you for this question, because it is an interesting question. Okay, it is the connection between TMD and high energy factorization is an important thing. It is in the large KT, there is a connection established in the large KT limit between unpolarized and linearly polarized TMD and the BFKL unintegrated Gluon distribution. But according to my knowledge, this relation is established at leading log. I don't know how it's work at next to leading log. So I am a bit conservative on this, and I will say that this connection is still a matter of investigation.
Okay, so my question, the next question is, usually exclusive processes in the collinear framework depend on GPDs and not on TMDs. So I don't understand the connection between these UGDs and GPDs. Well, maybe what I'm trying to say, let me ask this question instead. Are you able to describe the transverse momentum dependence of the outgoing state, the rho-meson? Can you describe its transverse momentum dependence?
Yes. Okay, when you let me go to the rho-meson case, in this way, In principle, yes. Here we are integrating over the whole spectrum of KT. But if one wants to be more exclusive on the KT spectrum, but also rapidity spectrum, can cut this integration, and then one becomes sensitive to a given region of KT. This is the answer to the second part of your question.
Right.
But yes, please.
So the KT here of the outgoing state, does it come from these UGDs, or because the way I usually understand it is that the transverse in exclusive processes, the transverse momentum acquired by the final state is related to the impact parameter of the target, of the proton or the nucleus, right? It's conjugate. That's why one can have the tomography and so forth. But here it seems as if it comes from this unintegrated Gluon distribution itself.
Yes, and also by the fact that this impact factor actually is nothing but an off-shell matrix element.
Right.
And in this regime, the off-shellness is given by the virtuality. So in principle, here everything is KT factorized and everything is KT dependent. As usual, here we are inclusive on the emission of the KT, so we integrate over the whole spectrum. But in principle, one can be more sensitive. But let me say something more about the connection between GPDs, etc. What you say is true and can be source of confusion. In this case, since we are neglecting skewness effects as small x, the UGD enters directly in the imaginary part of the amplitude, which is dominant with respect to the real part, because it's suppressed by one of the energy, or 1 over energy, if I recall correctly. And then in this case, you access exclusive processes directly via the UGD in the amplitude. If we want to calculate cross-section, as we have done, we simply need to square this amplitude and build cross-section. So the UGD entered twice in the description of cross-section, and this is in some sense analogous to GPDs, but this corresponds to the small x limits. The thing is that in this KT factorization, you can describe both exclusive and inclusive processes with the same kind of distribution. One, in this case, in the exclusive case, it goes to amplitude. In the other case, directly to cross-section via the optical theorem.
Right. So just so that I understand this correctly,
yes,
the non-diagonal nature comes in the impact factor solely, not on the unintegrated Gluon distribution. Is this correct?
Yes. In this case, this is correct. This is a difference between the GPD case. Yes.
Okay. Thanks, Francesco.
Thanks.
Thank you. Let's thank Francesco again. Now we are moving to the next speaker. Next speaker is Arthur Bolz. Okay.
Hi. Can you hear me?
Yes, we can hear you. Okay, go ahead.
Okay. So thank you very much for kind of having me here, and I'm quite happy that I can present an exclusive pi and rho-meson photoproduction measurement that we did at HERA with the H1 detector, and that we could publish last year. We've already presented preliminary results on this 2 years ago on DS. I will give a short introduction and present the measurement and some interpretations of the measured kinematic cross sections in the context of redshift theory. Okay, so I don't think I need to give a broad introduction here in this setting. So we study vector meson photoproduction. So we have photon oscillating into a vector meson, which can then interact strongly with the proton in this case. So this allows us to study strong interaction with kind of photons, and then in the soft regime where we cannot apply perturbative QCD. And then the characteristics are kind of in this redshift theory picture. The exchange is done by a color singlet state, which would be the regions or the Pomeran in the high energy range. And then experimentally, we of course observe these large rapidity gaps between the outgoing scattering systems. The interesting observation here is that for these soft diffractive cross sections, when we look in the high energy range, we observe that the cross sections of vector meson production, but in general hadronic scattering, rise with the energy. So what you see on the plot on the right is just an overview of vector meson photoproduction cross sections where you see this rise with the energy W. A lot of these measurements were actually done at HERA, in particular in this intermediate energy range. The energy rise in this redshift picture is actually characterized by the redshift trajectories, in particular the intercept at t equals 0. The other characteristic of diffractive cross sections is that if you look at the dependence on the momentum transfer t at the proton vertex, you observe typically steeply falling distributions, which typically are exponentially falling. So we do the measurement using data collected with the H1 detector at the HERA Electron-Proton Collider. HERA was operating until 2007 and colliding protons and electrons or positrons at a maximum center of mass energy of 320 GeV. In total, there was like half an inverse femtobarn of integrated luminosity to collect by two large general purpose detectors, H1 and SUS. And as I said, we use data from the H1 experiment. H1 was just, as you know, a large multipurpose detector having in particular very good colorimetry covering the full solid angle, then good tracking in the central region. What we had in H1, which is kind of important for this measurement, there were various forward detectors for the measurement of the scattered proton, both for the elastic and proton dissociative case. So we want to measure diffractive rho photoproduction cross sections. Here we have one or several challenges. So first of all, the rho-meson, it decays into a pair of charged pions. So a priori, we only measure the pi final state, and there's other contributions to it. So we can have other vector mesons decaying into pions. We can have other exchanges than the Pomeroy exchange if you're interested in that. And most importantly, we can also have a non-resonant pi production. So there's lots of irreducible backgrounds that if we want to measure the rho meson production cross section, we need to kind of get rid of or take care of. The other problem is, of course, we use the electron at HERA as a photon source. So a priori, we get virtual photons. So if you want to study the photoproduction regime, we need to go to very small virtualities Q square, such that the proton becomes quasi-real and we can extract photoproduction cross-section from it. And finally, we need to distinguish between elastic and proton dissociative scattering, which are particularly challenging to separate experimentally. So how do we do this experimentally? So how does pi photoproduction look in the H1 detector, just on a very simple level? So first of all, if we want to study photoproduction events, we kind of require that the scattered electron is undetected. And just by the acceptance of the detector, this means that we restrict our data to Q squared smaller than 2.5 GeV squared. And then we want to study this diffractive scattering. So also the proton is scattered in very forward direction and mostly leaves the detector undetected. So all that we remain with is just two oppositely charged central back-to-back tracks corresponding to the two pion pairs. And they typically have very small transverse momentum and very small momentum overall. So that typically they don't even leave any signals in the colorimeter, but we really have only the two tracks. So then there's obviously a lot of challenges with measuring this kind of topology. So first of all, since we only have tracks already on the trigger level, we need to rely on track information. Luckily at the H1, we had this level 1 FTT track trigger. Then as I said, we need to distinguish elastic from proton dissociative events. So this we did for this analysis by tagging the proton dissociative events with several of these forwards detectors that I mentioned before. Because we do not reconstruct the scattered electron and only the two pions, we are kinematically under constraint, which results in a deteriorated resolution of the reconstructed variables, which we also need to consider. And because we rely so heavily on the central tracker for this analysis, we are susceptible to lots of backgrounds with processes with neutral particles, or where some of charged particles lie outside of the restricted tracker acceptance. So let's have a quick look at the data set. So we used data collected in 2006 and 2007 only. The reason is just the availability of this track trigger that I mentioned before. And we also only have like a small subset of the total H1 data corresponding to 1.3 inverse picobarn, which is mainly because the trigger is heavily downscaled. Nonetheless, we have a very large data sample of pi events, which corresponds to roughly 900,000 selected pi pairs. What you see in the plot is detector level distribution of the reconstructed invariant pi mass. And you see we have a very nice peaking signal from the rho contribution at 770 MeV. We have in white the elastic and in green the proton dissociative component. And then there's various smaller but non-negligible reducible background. So they mainly come from vector meson production of other vector mesons, where some of the final state particles are missed or misreconstructed. The data is modeled with the different Monte Carlo samples, which are heavily tuned to describe the measured data distributions. Okay, a quick word on how we determine cross-section. So we pursued a quite complex unfolding procedure where we kind of try to map the truth level distributions on the reconstruction level. And on truth level, we distinguish signal elastic pi-pi and signal proton dissociative pi-pi, which can then migrate on detector level to various control regions that we define using forward information. In addition, we also have control regions for the various background components, which we use to normalize and subtract the background processes in the unfolding. So the unfolding in particular also corrects for the detector efficiency and resolution effects, and as I said, most importantly, separates the elastic from the dissociative contributions. Technically, this is done in a template fit using the T-unfold package. On the right side, you see the fiducial phase space of our measurement. In particular, we measure in the energy range from 20 to 80 GeV, T smaller than 0.5 GeV, and we extrapolate from Q squared smaller than 2.5 to Q squared equals 0 by normalizing our measured EP cross-sections to photoproduction cross-section using an effective photon flux following the Weizsäcker-Williams and VDM approach. One thing to consider is that for the proton dissociative cross-section, we only measure in this fiducial phase space where MY is smaller than 10 GeV, which is important for the interpretation of the results. So a first result is shown here. So this is now the unfolded cross-section as a function of m pi pi. Now we have separated in red the elastic and in green the proton dissociative component. Again, we see the pronounced rho peak here at 707 MeV, and there's also a higher rho resonance at around 1.6 GeV that we see. On the right side, these are just some numbers. We don't need to go through all the details. So these are the fiducial cross-sections and split up of the systematic uncertainties. So we mainly have normalization uncertainties related to the tagging coming from the colorimeter and large rapidity gap requirement, and then from the trigger and trigger correction scaling factors that we need. So next step, we want to kind of extract rho cross-sections from the measured pi-pi cross-section, and we do this by kind of parameterizing and fitting the invariant pi-pi mass with a Serding-inspired model. So here we kind of have amplitudes for rho, omega, and non-resonant pi-pi production, which are added on amplitude level so that also interference effects are taken into account. On the right-hand side, you see kind of an example of this plot where you see that we can have quite a pronounced interference effect from this model, and then we could just define the rho cross-section as the integral over the rho component to the model, contribution to the model. So this is kind of a fit of this model to the data. We restrict the mass range so that we can neglect in particular the high mass resonance, and you see then the model describes the data quite nicely. And we see what we already know is, right, we are dominated by the rho resonance, which is skewed heavily by a strong interference effect with the non-resonant component. What we also see, which I think is very cool, that we have this steep edge on top of the rho prime peak, which comes from the omega contribution, which also leads to this steep interference effect. And the same for the proton dissociative component on the right. And some numbers are again summarized here on top and compared to the PDG values. Also here, I don't think we need to go through the details. Now, in order to measure in the next step kinematic dependencies of the rho cross sections, we kind of measure the mass distributions in kinematic bins of W, T, and then W and T. So W and T two-dimensionally is shown here. We again fit all these mass distributions and extract the rho cross section to measure these kinematic rho distributions. First result is shown here. So this is kind of the energy dependence of the rho cross section. Here we compare our data with previous measurement, for example, from fixed target experiments and then previous HERA and LHC measurements. And we see our data very nicely fits this gap in the intermediate energy range. We parameterize the measured elastic and proton dissociative cross-section with a simple power law, where the parameters are given here. And particularly one thing to consider is that the elastic cross-section rises slowly with energy as we would expect, but the proton dissociative component falls. And this, one has to be a bit careful when one interprets this, because the cross-section for the proton dissociative component is quite heavily shaped by the phase space restriction, MY smaller than 10 GeV, which in particular suppresses the cross-section at high energy. We also did a fit of all the available elastic data with kind of two power functions corresponding to a Pomerón and Reggion contribution. And there we see that if we do this, the Pomerón parameter is raised a little bit, which kind of suggests that in the measured or in the considered measured range, we see a small but non-negligible region contribution. The next result, what we also measured is the T-dependence, of course. Again, shown here for the elastic and proton-dissociative component. We also parameterize this with this function given here, which kind of interpolates an exponential.
You have 3 minutes left.
Thank you. At small t and going to Paula at larger t. We see that towards larger t, we have deviations from the pure exponential behavior, which are more strongly for the proton-dissociative component. And then we measure the B parameter, which is consistent with previous measurements. And of course, we observe a much harder T-spectrum for the proton-dissociative component. The final result that we measured is a kind of two-dimensional dependence of the rho cross-section as a function of energy in T. Again, this is shown here where we have the T-dependence plotted in various energy bins for the elastic and proton-dissociative component. We parameterize, again, these 2D cross-sections with the T-dependence that I introduced before, and then a Regge ansatz for the energy dependence, where we introduce a Regge trajectory for the exponent. And we don't just use a linear trajectory, but have this more complicated function, which kind of interpolates a linear function at small t, but becomes a constant value towards t going to infinity. Right, so the fit of this model to the data is shown superimposed on the data. And then to visualize the trajectory that we get, the curve f of t is shown on the right-hand side of the plot. And to put it a bit into context, what we do is we compare it to the individual power parameters that we would measure for the energy distributions in all the different T bins, which we kind of extract by independently fitting all the energy dependencies in the measured T bins. Right, so these are the data points here, and the curves that you see, they are not extracted from a fit to the data points, but rather from this 2D fit. So the measured intercept is given here, so it's 1.065, and the measured slope. And we do not see significant deviations from the linear from a linear trajectory. However, there are some indications that there might be deviations in the considered T range. So with this, I come to the final slide. So I talked a bit about a measurement of pi and in particular rho photoproduction that we did at HERA. So we measured up to 3-dimensional pi cross sections and then 2-dimensional rho cross sections that we parameterized with models and fitted with models to extract more fundamental parameters. In particular, we measured the leading Regge trajectory. And again, the interpretation is a bit more difficult. So the parameter for the intercept and for the slope are again shown on these left two plots and compared to previous results. We see that the intercept we measure tends to be a bit on the low side compared, for example, to the Donaghey-Lanzov expectations, whereas the slope describes the DL value quite nicely if one takes into account a possible deviation of the linear behavior at larger t. And one interpretation why the intercept that we measure is a bit towards the low side might again come from a small but non-negligible region contribution in the considered energy range, which unfortunately we cannot constrain with our data, but which might lower this intercept a little bit. So with this, thank you very much for the attention. If you want to read more, we have a publication in EPJZ, which you can read up all the details. And of course, if you want to analyze our data yourself, we provide all the data on the H1 data webpage and hopefully also in HEP data very soon. Thank you very much.
Thank you, Artur, for this very nice talk. Thanks. The first question we have from Antoni.
Yeah, beautiful data. Congratulations. My question is, what do you do with this continuum, this DEC effect or your Sodding parameterization? For each differential point, you subtract this effect, or?
I mean, we don't really
subtract. Or you show it together,
right? We do. I mean, for each differential point, we kind of measure the mass distribution and fit this model that I briefly introduced. We fit it to the mass distributions in all the kinematic bins.
And then you show the data only for this pure rho-meson.
And then what I showed in the following is the rho contribution integrated out.
I think it was not always done as you did, right?
So
before.
I mean, I mean, for the fixed targets, I don't know, but for the previous HERA and also this shown CMS result, it was done in a similar way. Of course, there's always the question how one exactly defines this model, and then the rho cross section, of course, depends a bit on how one defines this model and extract it. So there's some inconsistency there, but in principle, all the data that is shown here is really rho cross sections and not pi cross sections.
Thank you.
Thank you. Okay, I don't see more questions or comments. Let's thank the speaker again. And now we can go to the next talk. The next speaker is Valeri Pozdnyakov.
Good evening. Just a question. Do you hear me?
Yes. Could you share?
So I will share slides. Just a minute. This one.
Yes.
Do you see slides? Okay.
Yes, we can.
So I would like. At first, I would like to say thanks for to the organizers to provide the possibility to present our results obtained with ALICE detector for different kinds of collided ions. So I will speak about a study of so-called ultra-peripheral collisions of heavy ions when we have a it's schematically drawn here. If we have the impact parameter between two ions smaller than sum of their radius, so we have only mostly a possibility for the reaction to be photon induced reactions. So actually we can split this type of the reaction in two classes: two photons, which are I would say a background for us. We don't measure two photon contributions, but our aim is to measure rho-zero produced in photonuclear reaction. So, for LHC, we have unique possibility to study with very large energy and with sizable, with a great large charge of the ions. So the cross section of these photonuclear and two photon reactions as well is quite, I would say, huge. So what we have in this reaction, we have a photon which fluctuates to a vector meson, rho-zero in this case, and then rho-zero scatters off on a target azicoherently of whole nuclei, and then transverse momentum of vector meson is quite small, or incoherently when we have a transverse momentum one order or larger. Another nice feature to study UPC at LHC is that for large charge of the ion, we had got huge photon fluxes, and in that case there is a quite sizable probability to get additional exchange by the photon between ions, and then we can get electromagnetic nuclear excitation with subsequent neutron emission, and our detector is equipped with a colorimeter which can detect these neutrons. So for you, actually the main goal, the main aim of UPC studies at LHC is to study Gluon shading, possible Gluon shading in nuclei. And there are at least two very nice UPC review which can be looked. So Alice detector at LHC composed from many different kind of the detector, but for our study the main is TPC, time projection chamber, to reconstruct rho-zero decays into pions, and also we have some trigger detectors which allows us to efficiently collect the data, and also 0-degree calorimeter to detect the neutrons from electromagnetic dissociation. So on this slide you see real events detected by Alice. So Alice event display for forward muons, so nothing in the detector, just 2 muons detected in muon arm of our experiment. And for barrel, for central region of the detector, you see TPC and in tracking system, and actually this plot nicely illustrates what's going on in the detector. So we have a back-to-back topology in transverse plane, and also we have some Lorentz boost to the across to z-axis, so it's quite clean topology. And main feature of ultra-peripheral collisions are that we have only decay products of vector meson detected in the setup, and also these decay particles have a transverse momentum balance well balanced in the transverse plane. And I would say that it will be the talk of Thomas Herman on GPSI production in UPC, but here I speak about rho-zero. So at first we we measure coherent rho-zero production in LED at 5 TV of square of root S. So the motivation of this study is that rho-zero cross-section of rho-zero production is so high that we can move to the study the approach of so-called black disk limit of QCD. So we collected something like 60,000 events, reconstructed events, which pass the criteria that both particles are in central domain, balanced transverse momentum of these two particles, and overall experimental efficiency is quite high for this kind of events. So we fit we correct our distribution for acceptance and efficiency, and then we fit the distribution by Barrett-Wigner for resonance shape, and constant term not shown here for direct pair production, so interference between rho-zero and direct pi plus pi minus production. And also we left with some background coming from gamma-gamma interactions, mainly to the muons. So after the fit, we obtained 3 measured points, and this is a reflection of these 2 points. So for central production, we measured coherent rho-zero photoproduction, and as you can see, we are limited in our accuracy. We are limited by systematic correlated systematic. And also you see few predictions for the case for whole sample without any splitting for rho-zero. So you can see that our data within systematic uncertainty which is around 7-8 persons. We are in agreement with a few models, except for Starlight model, which is a quite low with respect to the data. And also this model CCKT has a quite large band, but in some sense we are lower than the prediction of this model. So we made a conclusion that actually our data have some I would say some beta agreement for so-called Guzey-Zhalov equation model. So now I move to the feature which I already described, namely we can get the possibility to get in the event some neutrons coming from electromagnetic excited ions. And for this, ALISA is equipped with 2 colorimeters, which are located more than 100 meters from the center of the collision, and with a quite nice resolution, time resolution, and energy resolution. And if we draw energy in one arm of our ZDC, with respect to second one, you can see a nice plot which illustrates that the feature that here we have no neutrons, and then 1 neutron from one side, 2 neutrons from one side. So if we make a projection, you can see the possibility of our detector, of our setup, to detect 1 neutron, 2 neutron, 3, and then resolution became worse. So we split our sample into 3 different classes, which are for different neutrons, neutron topology. Namely, we have a large portion of the events without any neutrons in our detector. Then we have a sample with 1 neutron, with the neutrons from one side and nothing from another. And also we had got some essential, sizable, I would say, data sample with neutrons detected in bus side of ZDC. So you can see the comparison with the model, which now the models include electromagnetic dissociation. And as you can see, again, our data are limited by systematic uncertainty. Unfortunately, it's unavoidable. And at the same time, that's nice to mention that our data actually
Valeri,
yeah,
you have 3 more minutes.
3 more minutes, okay. With different classes of ZDC. So now I move to next point of the presentation, namely, if we have a look at large invariant mass, pair invariant mass, we see well-balanced events for this domain, and we fit the data by so-called star-like approach, and we consider that the data that we see resonance-like structure with a mass something like 1.7 GeV. So now we made the same study for xenon. Actually, LHC collided for the first time xenon ions, and we made the same strategy, the same technology for the data analysis, and we see the rho zero peak. We again fit with the same the same composition, and we measured rho-zero coherent rho-zero production in xenon-xenon ultra-peripheral collisions. Now we have a point below all calculations, but again the uncertainty unfortunately is quite large. So we also fit our data for gamma xenon, gamma LED, and also H1 data with some power law model, and we found that slope parameter is around unity. So now last slides for our prospect to study LED UPC with round 3, which will come next year. So we made an essential upgrade of the detector, which allows us to take the data in so-called triggered and in the continuous readout mode without any trigger. So we expect very large data samples which we can collect with around 3 and 4 data. So you see, for 0 we expect something like 5 or 20 billions of the reconstructed events for different central domains and forward domains. Also, we estimated our possibility to detect proton-antiproton events. And so now I move to the conclusion that we analyze rho-zero photoproduction in high energy gamma nuclear interactions to search for black disk limit. So we measured rho-zero in both LED and xenon at approximately the same energy. And we found, we measured coherent rho-zero in LED and found this in agreement both with a model based on color dipole approach and Gribov-Glauber shading approach. And for the first time, we measured cross-section for different neutron emission classes. Also, we see some white resonance-like structure with a mass around 1.7 GeV. And also we measured, for the first time, we measured coherent photoproduction in xenon UPC. And our estimation for vector Meson photoproduction in LED UPC for rounds 3 and 4 are quite promising. Thank you for the attention. That's all from my side.
Thank you, Valeri, for a very good talk. Now, okay, I see we have question from Antoni.
My question is, this final number which you have shown in this very last slide, is it with without condition on neutrons, or this is with a condition on neutron?
You mean this slide?
No, there was such a data point of Alice and different distribution of different models in rapidity. This one. No, just I don't know in which direction. No, 1 point and rapidity distribution.
You mean LED or xenon?
No, I think it was LED.
LED. So for LED, it's a final, it's a published point. It's a published result.
But this is with neutrons, or?
This plot correspond whole sample without splitting.
Without splitting into...
Yeah, it's without splitting, and on this plot you see with the splitting, without
no,
neutrons.
My question is also, do we understand these different categories, 1, 1, 1, 2, 0, 2? If these ratios, can we describe those ratios with the models, these nuclear models which are on the market?
Yeah, we combine actually authors of the model combine their calculation with the electromagnetic calculation, which electromagnetic dissociation was measured at the beginning of the LHC. So we can believe on the results. We can believe the results of this electromagnetic dissociation model, and then we just we just look. For instance, these events are 0 neutron, 0 neutron, no neutrons from both sides. And then we have some events with neutrons from one side and nothing from another.
I understand. Yes, yes.
Yeah. So it's a technology which we use. And
but in principle, you could check those models from your measurement.
To check from what?
These calculations.
But actually, we do this. So it's our data. And this is this is a model calculation with at least one neutron from one side. Xn means that more than 0 neutrons, 1, 2, 3 neutrons.
Yeah, but I see that these different models change depending on this category of number of neutrons.
Yeah.
So models don't completely describe those ratios, because sometimes are above, sometimes are below.
Yeah, yeah. But actually only these points are above all models. But for 0 neutron, 0 neutron, and for neutrons with both side, we would we are happy to see from our point of view nice agreement.
Okay, thank you.
We have another question from Spencer.
Actually, this was just a comment about Antoni's question. You know, the model, you know, the data is very consistent with a model of factorization where you have the rho production is separate from the nuclear excitation. And basically, they occur by separate photons, or for Xn, Xn, 2 separate photons, and they're linked only by an common impact parameter. As Antoni mentioned, you know, the 0n Xn is a little bit above the data. That would be, there's some room there for incoherent photoproduction to be sneaking in.
Yeah, Spencer, yeah. Actually, as far as I remember, in the paper we mentioned that this can be source of small, or let's say disagreement, small excess of the data over calculation, because we have some incoherent part.
Thank you. Now we are moving to the last talk today. The last speaker is Heikki. Yes. Okay, you can start.
Okay, thanks for this opportunity to discuss recent work I have been doing with Kosik, Farid, and Björn. So we want to study exclusive shape-psi or photon production. So EP going to photon or shape-psi and proton. And of course, you all know why exclusive process is. So first of all, there is no net color transfer from the target to the produced vector particle. So very roughly, the cross-section is like Gluon squared. So this is highly sensitive process. And because you can measure the total momentum transfer, you get access to spatial distribution of partons, because the momentum transfer is the Fourier conjugate to the impact parameter. Now, in this work, we wanted to study this process differentially in both momentum transfer or squared momentum transfer T and the azimuthal angle between the electron plane and the plane where I have the produced photon or vector meson and the outgoing proton. So my results will be shown as a function of this angle, which is illustrated here in this cartoon. And the motivation is that with more differential measurements, it should be possible to somehow obtain more detailed information of of the small structure of the target. So in the paper that I cited on my first slide, what we first do and how we approach this problem is that first we calculate the cross section for or scattering amplitude for virtual photon coming in, splitting to a dipole. This dipole interacts with the target color field, and then final state is again a virtual photon. But now the initial virtual photon had a polarization lambda, and the outgoing virtual photon had a polarization lambda prime. Now, and yeah, the D here is just the standard dipole scattering amplitude that tells you how the dipole interacts with the target. Now, I can look at, for example, scattering amplitude for the case where the incoming photon and outgoing photon are both longitudinally polarized. This is the M00 that's illustrated here. And the only thing I want to point out is that this is approximately only probing the dipole target scattering amplitude, the part of the dipole amplitude that does not depend on the angle between the dipole size and the impact parameter. And then if this blob here on the right is the proton, then you can see that the impact parameter points from the center of the proton to the center of the dipole, and then R is the orientation of the dipole. And then if I look at, for example, a case where my initial virtual photon has a transverse polarization, and the outgoing photon also has a transverse polarization, but this polarization flips, I get must be denoted by m plus 1 minus 1 scattering amplitude, and then this is highly sensitive to the angular dependence of the dipole. So basically, it matters if the dipole prefers to scatter parallel to the impact parameter or perpendicular to the impact parameter. And then, of course, we also calculate all the other scattering amplitudes with all the possible polarization combinations. And finally, when we calculate observable, we can take the outgoing photon virtuality to 0, and then it's a DBCS, or we can use some phenomenological model for the vector meson wave function and calculate shape-side production. Okay, let's take a little bit closer look at this example of the scattering amplitude for the case where the polarization state flips. So this is illustrated here again, the same equation that we had on the previous slide. And there are actually now two components that bring in some correlation between the incoming electron and then the momentum transfer in the scattering process. First of all, you have to remember that the dipole size or dipole orientation R, that knows something about the electron, because we had the electron emitting the photon that splits to a dipole. So that's why the dipole size knows something about the electron. And then in this particular scattering amplitude, we have this kind of phase factors. So there is an angle between the dipole orientation and the momentum transfer vectors multiplying the dipole amplitude. So basically, you immediately notice that something like a structure like that is highly sensitive to the angular dependence that you have in the dipole scattering amplitude. And that contribution to the azimuthal correlations we call intrinsic in this work. And this actually can be related to the elliptic Gluon GPD, as was nicely shown in this paper. Then there's a second contribution that also gives us some azimuthal correlations also when I finally go to the cross-section level. And that's because there is another phase factor, the so-called off-forward phase, where also the dipole size couples to the momentum transfer. And this we call a kinematical contribution because it doesn't really come from this intrinsic QCD dynamics. And this can be somehow intuitively understood that because when you have a momentum transfer, your propagation axis changes, and that mixes also different polarization states. Okay, so then once we have all these required scattering amplitudes, we can go to the cross-section level, include the photon flux from the electron, and then we can write the total DVCS cross-section in this form, where we have a part that does not depend on the angle between the, that does not depend on the azimuthal angle between the electron plane and the plane where we have produced the real photon. And then we have some contribution that comes with the cosine phi modulation. And we have a combination or contribution that comes with cosine 2 phi modulation. And let me focus on the last line here. So this cosine 2 phi modulation, the coefficient is exactly this scattering amplitude m plus 1 minus 1 that I was highlighting on the previous slide, which is directly sensitive to these correlations between the dipole size and the impact parameter in the dipole scattering amplitude. And that also means that this contribution is sensitive to the elliptic Gluon GPD or even some parts of the Wigner distribution. Okay, so let's first demonstrate using kind of a toy model that really is the fact that if I have some dependence on the dipole orientation in my dipole scattering amplitude, that really has a big effect at the cross-section level. So we can use a kind of a GPW-inspired toy model where I can tune on or off these angular correlations. So if C is 0, then there is no dependence on the orientation in the dipole amplitude. And then if I have some non-zero C, then the dipole prefers to scatter when it's parallel to the impact parameter. And let me walk you through the busy plots that I have here. So this is the DVCS cross-section as a function of squared momentum transfer. The solid black line shows the part of the cross-section that does not depend on this azimuthal angle between the electron plane and the plane where the produced photon goes. And then what I'm showing is the coefficient of the cosine phi part of the cross-section. So this dashed line here is exactly the part that multiplies the cosine phi in this expression for the total DVCS cross-section. And similarly, that dotted line is the coefficient of the cosine 2 phi term. And now what happens when I turn on the angular dependence in my dipole scattering amplitude, I get the right-hand side plot where the most striking effect is that now the cosine 2 phi modulation in the cross-section becomes actually very large. So this DVCS cross-section clearly is sensitive to the details of the angular dependence in the dipole scattering amplitude. But of course, in order to make some realistic predictions for the EIC, we don't want to use this kind of a toy model where we plug in these correlations by hand. So what we do is that we use a CGC setup where we first, at initial Bjerken X, we use an MV model to describe the proton structure, and then we do a small X Tim-Walk evolution when we go to some smaller X, where we actually calculate the cross section. And then we can do this evolution event by event and then obtain results by averaging over some number of configurations. And this plot on the left illustrates that what we actually can calculate is, for example, how does the dipole target scattering amplitude, now it's denoted by n, not the d, but anyway, it's the same quantity, how it depends on the angle between the dipole size and the impact parameter. So this actually comes as a prediction from this setup, and we can also calculate the Bjerken X dependence by solving Tim-Walk. Of course, we can check that our setup is compatible with HERA data. So here I'm showing on the left the DVCS data, now only no dependence on the azimuthal angles, just the T spectra, on the right the shape size spectra, and the agreement is quite good. Okay, so let's then go to our actual predictions for the EIC. I mean, the question is if we actually can expect significant azimuthal modulation, something that could in principle be measured. That would be very interesting. Okay, so the left-hand side shows again the same spectra that I had from the toy model, but now from the full CGC calculation. Again, I have the part of the cross section that doesn't depend on the azimuthal angle, and then the coefficients of the cosine phi and the cosine 2 phi modulations. And maybe it's easier to look at what when we extract V2 and V1. Now, these Vn's, they are defined as an expectation value of cosine n phi. So, and then they basically quantify how large modulations there are. And let's now focus only on V2 in the interest of time. So the black line here is V2 at initial Bjorken X at 0.01, where we initialize.
3 minutes left. 3 minutes left.
Yes, and we find that we have like 5 to 10% V2, so quite significant modulation. And then when I go to smaller X, then the Chimok evolution reduces this by factor of 2 or so. And all this is in the EIC kinematics. Then we can do the same exercise for shape psi. Again, if we just look at the Vn plot on the right-hand side, we find that the V2 is a little bit smaller, say of the order of 5%, but hopefully still something that could be measured. And again, it decreases as a result of Chimok evolution. Then, of course, we can also ask the question what happens if we replace protons by nuclei, and then the spectra are again now shown for DVCS on the left and for shape psi production on the right. And you see that the cosine phi and cosine 2 phi modulations are actually very small compared to the part of the spectra that doesn't depend on the azimuthal angle. And this we can understand because in this setup, basically the dependence on the dipole orientation comes from the density gradients in the target. So basically, when you rotate the dipole, if the dipole can see the density gradients, then you have some non-trivial angular dependence. And with a large nucleus, of course, there are very small gradients, and consequently only also the azimuthal modulations in the DVCS and shape psi cross section are very small. And the same effect actually explains why the Chimok evolution suppresses V2s with proton targets. Finally, we also extended this analysis to incoherent diffraction with the motivation that maybe it's possible to more precisely probe the fluctuating substructure of protons. Basically, the motivation being that, I mean, as you have already heard in this conference, you can use coherent and incoherent data to constrain the proton substructure fluctuations, because the incoherent cross-section is basically the variance of the amplitude, and it's sensitive to how large fluctuations there are, but maybe it could be possible to study also somehow details of this, but what kind of fluctuating geometry there is. Now, we didn't go that far yet. What we did is to calculate incoherent DVCS and incoherent shape psi production, and then again extract the Vn fluctuations. What I'm showing here is the V2 on the left for DVCS. The solid lines are obtained with the fluctuating proton structure, and the solid lines have no fluctuating, sorry, the dashed lines have no fluctuating geometry. And when we go to high enough T, say above 0.5 GeV squared, one is then sensitive to small enough distance scales to actually see a significant effect from the substructure, both in case of DVCS and in shape psi production. So we have calculated the azimuthal angle modulations in exclusive photon and shape psi production, identified two sources for this modulation. Somehow the more interesting one is what I call intrinsic, and it's related to the elliptic Gluon CPD also. And then we have one which is of the kinematical origin. For the EIC, we predict quite significant, say 5 to 10% modulations that could be hopefully measurable. And then we also calculate how these modulations depend on center of mass energy and what happens when you go to nuclei. In that case, the modulations become very small. So of course, in the future, it would be interesting to study different fluctuating geometries. And then there are also some other very important and interesting developments that could have effect in this work or in this context, but I'm not going in this in detail yet, but please see Adrian's and Yannis' talks today and tomorrow. Thank you for your attention.
Thank you, Heikki, for a very nice talk. Any questions or comments? Bowen, you can go.
Oh, thanks. Heikki, very interesting talk. Can you comment a little bit more on this the numerical significance of this off-forward phase factor? Because we were always wondering how large this phase factor numerically is. Thanks.
So I mean, I don't remember by heart what's the effect on the angle independent part. Then for the modulations, then okay, it's a little bit quantitative question, depends on the observable also. But let's say quite in case of say okay, this is a toy model, but maybe I go to so for example here I had the cosine phi modulation, and in that I think the dominant source was, or at least there was a significant contribution from this off-forward phase. Then if I go to shape side production where my dipole is smaller, then I mean, of course, the off-forward phase couples the dipole size. So then if I have a small dipole, then this also has a small effect, and that you see that especially the cosine phi modulation is basically negligible in this case, because that is really driven by this off-forward phase, and then with small dipoles it doesn't have such a large effect.
Oh, does it make a big difference also for this unpolarized for the let me say symmetric part, the average part?
My impression is that it's not a significant effect, but I don't have exact numbers now.
Okay, thanks a lot.
Okay, thank you very much. Thanks the speaker again. We are finished. I'd like to thank all the speakers today for very interesting talks, and all of you for your participation, your questions, and your comments. Thank you very much, and see you tomorrow.